All right, so let's resume where we were talking about numerical models. Again, just remembering the problem that we have. We have this sphere, and we've dropped the sphere in at some time. We introduced a transient boundary condition where the ambient temperature is changing as a function of time. And we're trying to solve a model where we just predict the temperature of this body as a function of time. Again, we've made this 0D assumption, or the lump capacitance assumption. And that says that this is only a function of time and not a function of coordinate within the domain of the sphere, right? The entire sphere is at a single temperature, right? And then the goal of this, the numerical methods, is to get to this state equation, right? This thing here, which, given the current state of the system, some temperature and some time, we can predict the rate of change of temperature with time. That's the definition of state equation. Okay, so last time we got through talking about a couple methods. I think we talked about Euler's method, we talked about Heinz method, and we talked about Runge-Kutta, right? The one with the 4 different predictors. In each of these different methods, the differences between them are kind of how many times you're evaluating the derivative and where you're evaluating the derivative with respect to time. Okay, so let's pick up again on this numerical, and let's talk about the next one I have here, which is called the fully implicit technique. Okay, so the fully implicit technique, if you remember, we were kind of going through and classifying these things. So this is a first order technique. Okay, first order means we're going to be evaluating the derivative once, and then instead of being explicit, as the name would imply, it's implicit. Okay, so what does this mean when we're actually evaluating? What does it mean to be implicit? Well, implicit is saying that now, instead of dt, temperature d time, being a function of what's happening right now at this current time, this current moment in time, it's actually a function of what's happening kind of across the time step. And specifically for the implicit method, it's dt is predicted using the slope at the end of the time step. Okay, so when we write this out, we would say t j plus 1, right? The time of the temperature at the next step is going to be predicted by taking the current temperature Tj and adding to that the derivative of temperature with respect to time evaluated at Tj plus 1 and time j plus 1. Okay, times delta T. And that's for, again, if we write this, for j equals 1 to m minus 1. All right. So when you're actually evaluating this, I mean, if you go into ease and evaluate it, it's pretty easy to do that in ease because you can solve all the temperatures at the same time, right? Ease will solve everything at once. But if you're trying to do this in MATLAB, how do you go about evaluating the derivative of a temperature at the end of the time step when that's the thing that you're trying to use to predict the temperature? So let's walk through a little bit of how to do that. Okay, so let's actually write out the expression here. We would say Tj plus 1 is equal to Tj. And for this particular model, it is T infinity, which is a function of time, minus T at j plus 1. All of that divided by tau LC, or tau lumped, times delta T. And that's for our j that we wrote up there. Okay, so if we want to actually, like I said, we can solve this in ease, just plug this set of equations into ease and solve all those at the same time. That's not a problem. And if you want an example of that, you can look at the lumped implicit.ease file. It does that. If we want to solve this in MATLAB, we need an explicit way of writing this because you can't assign something that you don't know yet. Right? So let's write this out. So actually, what we would do is it's pretty straightforward. You can actually solve this entire equation. Right? So here's Tj plus 1 appears a couple times. We can actually just solve this equation for Tj plus 1. In this case, it's pretty easy to do that. So if we do that, we get what? So if we solve it, we get Tj plus 1 is equal to, in the numerator, it's Tj plus T infinity divided by tau lumped times delta t. And in the denominator, it is 1 plus delta t divided by tau lumped. So this is an explicit relationship for tj plus 1, right? Any questions on that? Right. So then we just take this equation, we plug that into MATLAB. Obviously, you need to say what tj0 is, or the first time step. You need to give it the initial condition, but then you plug it in, evaluate this for every step, and now you're able to solve using an implicit method. Now, as you go through and you have more sophisticated or more complicated, I'll say, models of what's happening as opposed to just this simple t infinity minus t, this equation here changes, right? This is not universal. This is for our specific problem. Because you're always going to need to solve for our specific problem explicitly in this way if you're using the implicit method. One way that you can kind of make that easier is, again, to go to Maple. So just plug in your t equation, and then you can just use Maple to solve that. Okay, so how does this one stack up compared to the others? So again, this is first order. So let's say we have m equals 11 nodes, m equals 11, which is I think it was 0.04 seconds. Okay, so that leads, in this case, to a global error of 6 degrees Kelvin. Okay, if you remember Euler's technique, our baseline was something like 8 or 8.5. So for this particular problem, it works out to be pretty much the same order of magnitude of error. So why would you bother going through this process? Well, if you're using an explicit technique can become unstable very easily. Right? You miss your prediction of temperature, and then your next evaluation of derivative tries to correct that, and then you're correcting again, and it just starts oscillating really wildly. So that's a problem with explicit. For implicit, it's actually very stable. So for a pretty small number of nodes, it's going to remain stable. You'll be able to get a reasonable solution. However, the solution itself can have error associated with it because it's first order. Okay, so but then for m equals 101 nodes, we would expect the error to drop by an order of magnitude. So it's 0.7 degrees Kelvin for this problem. Okay, so again, global error is proportional to delta t to the first power. First order technique, even though it's implicit. Okay, again, let's go through these and then I'll show you the MATLAB code. Any questions on this method? Yeah.
And you always solve the tj plus 1 like that, or is it sometimes that you might get implicit equations you have to use something like these?
You can solve, so the case where it would come up is if you have like material dependent properties or temperature dependent material properties, right? In that case, there's really no way, unless you have a really simple equation that you can explicitly solve, then you would need to use something like successive substitution, right? What we talked about before. Yeah. Oh, that should, yeah, I suck at drawing that. It's supposed to look like this, right? It's like this. Oh, that's 1. Delta t to the first power. So delta t to the first power. Oh, that looks like a 2. Delta t to the first power. There you go. Okay, so that's the implicit method. Next method that we're going to talk about is called Crank-Nicholson. So Crank-Nicholson is kind of like the implicit method. It's kind of like Heinz method. It's basically a combination of those things. So it's, let's see, it is first order. So it is first order. Oh, sorry, it's second order. It's second order. Second order. and it is implicit. Okay, we just talked about a first order implicit method. Now this is a second order implicit method. So what is the method? Well, we say if we're going to predict Tj plus 1, that's going to be Tj plus the quantity, the derivative with respect to time at Tj and time j, plus the derivative with respect to time evaluated at Tj plus 1, time j plus 1. And then the average of that, so delta t over 2. Okay, so we're taking exactly the same as the implicit method. We have dt dt at the end of the time step, but then we're taking the average of that with our kind of initial estimate. So it's just another data point that we're using to get a good estimate of what we think the derivative is going to be for these. Okay, for this one, let's see if we write it out. For our actual problem, it becomes Tj plus 1 is equal to Tj plus T. I'm just going to write T infinity shorthand there. We know it's a function of time. But we have to evaluate it at a certain time, right? So T infinity at Tj, at time step j, okay, minus temperature j divided by tau LC, which is a constant. Okay, so that's our first derivative evaluated at the current time step. And then we have our second derivative, which is T infinity now at time j plus 1 minus temperature at j plus 1 over tau LC times delta t over 2. Okay. So yeah, you can see now we do have Tj plus 1 appearing on both sides, so it's implicit. But again, this can be solved explicitly. Right? We could go back and solve this implicit equation to have an explicit relationship for Tj plus 1. It's still implicit because the formulation makes it implicit, right? The formulation is saying, let's look at both the beginning and the end. But we can solve explicitly for this equation. I don't know if I need to write, I guess I could write it out just for the sake of having it, but it's Tj plus 1 is equal to Tj, 1 plus delta t over 2 tau LC plus the quantity T infinity at Tj plus T infinity at Tj plus 1 times delta t over 2 tau lumped. All of that divided by 1 plus delta t over 2 tau lumped. Okay, and these are all for j is equal to 1 to m minus 1. So that's our explicit relationship there. Okay, in terms of how this method does for m equals 11, we get 1.1 Kelvin error. So it's better, right? Significantly better. 2 evaluations of derivative, second order. Okay, so for M101, right? Again, it's second order. So we expect the error is going to go down by delta t squared, right? So it's going to be 0.01 Kelvin for this case. So now you're seeing it's a really good accuracy on this. And because it's implicit, it's really stable, right? So there's reasons why people use these methods as opposed to the other ones. Yeah. Yeah, I mean, so if it's expensive to evaluate the derivative, right? If like computationally, if it's really expensive, let's say you instead of having a really simple analytical model for the derivative, let's say you have to run a CFD simulation or something to get your derivative. If it's really expensive, you might want to make sure that solution's stable. So you'd use the implicit method, but you'd rather just make an evaluation and move on. But in the end, I think, yeah, you probably, in almost 99% of cases, this is going to be better. Just takes a little bit more effort.
Like when I'm at my desk, like running CFD, I'm not thinking about dollars,
Well, it's not, it's, so when I say expensive, I mean your time,
Oh, okay.
right? Like you are you as an RA are an expense to somebody, but it's more like your time, right? Your time is, you have a week to do the task you're going to do. Do you want to spend 6 days of it waiting for your computer simulation to finish? Right. Or do you want to do something that's a little bit faster? So yeah. That's kind of what that means. Okay. So this is Crank-Nicholson. Let's actually look at these. So this is the last kind of the, what we call like the classical numerical methods. So let's actually look at MATLAB on these real quick.